So we did the solubility constants in the previous presentation where we calculated KSP and all that. Now we're going to see how to predict if you will have precipitation or not. So let's see how we can predict precipitation. Precipitation can be predicted by using reaction quotients. And you remember reaction quotients from equilibrium constant where we had QC. So here you can use QC or QSP for solubility product and determine that whether something is going to precipitate or not. So compare QSP to KSP. So here is a random equation where you have X as a salt, and then so you get these two ions in here. You calculate your QSP just like you would calculate KSP with m to the power of 1 because there's only one ion, and x to the power of n if you have more than one. And the I's here indicate initial concentrations, and it's really one of the little redundant things in there because most of the concentrations will be initial concentrations for you. So the way it works is that if QSP is less than or equal to KSP, okay, or really just less than KSP, then no precipitate is going to form, okay? No precipitate will form. Please think about that for a second, because precipitate formation means that you're forming the solid over here. So at one point, everything is going to be in aqueous solution, and then at one point, things will start precipitating out, forming a solid, which means you have too many of these ions, okay? And the solubility is not enough. And so therefore, they will start combining and forming a solid. So if QSP is less than KSP, then no precipitate will form, which makes sense because it means you can have more ions in there. When QSP is greater than KSP, then precipitate will form. Makes sense because it means you have a lot more ions in there. So then QSP is equal to KSP. It means you have equilibrium, and at that point, you also have precipitation going on. Precipitation again meaning that you're forming solid. It also means that your equilibrium is now in the reverse phase. So let's go ahead and look at a problem then for predicting precipitation. One form of kidney stones is calcium phosphate, all right, which has a KSP of 1.0 times 10 to the negative 26. A sample of urine contains 1.0 times 10 to the negative 3 molar calcium and 1.0 times 10 to the negative 8 molar phosphate ions. Calculate the QSP and predict whether calcium phosphate will precipitate or not. Are you going to form kidney stones or not? Really, that's what it's asking. So here is your calcium phosphate. Here is the dissociation. You get 3 calcium ions and 2 phosphate ions from the dissociation. So our KSP is calcium to the power of 3 and phosphate to the power of 2, and KSP is given to us, which is 1.0 times 10 to the negative 26. So we are calculating for QSP. Remember, the QSP is the same formula as KSP. So we're going to go ahead and use the concentrations over here. So 1.0 times 10 to the negative 26, okay, for, excuse me, my bad. For calcium ion, we have 1.0 times 10 to the negative 3. That is given to us here, and this is to the power of 3. And the concentration of phosphate ion is also given to us, which is 1.0 times 10 to the negative 8. And that is the concentration of phosphate ions in the solution, and that you will raise to the power of 2. And so then QSP is equal to 1 times 10 to the power of negative 25. So KSP is less than QSP, or you can say QSP is more than KSP. So if QSP is more than KSP, then you will form precipitate, okay? Because KSP is 10 to the negative 26 and QSP is negative 25. So 26 is smaller, okay, than 25. So which means you have a lot of ions over here. One thing I want to point out, and if you feel like you're going to get confused, you can mute me right now, or close your ears, all right? But anyhow, what I want to mention here is that when you have these coefficients here, the 3 and the 2, these are referred to here as the powers of the concentration. In here, we do not use the 2 and the 3 inside the brackets, okay, like we did for molar concentrations, because the concentration of ions is already given to us. We already know what the total concentration is, so you don't need to use the 2 and 3 for the X, okay, or the S, whatever it is, all right? And so therefore, you just use the concentration as it is and plug it into the QSP formula. Another example, exactly 0.400 liters of 0.5 molar lead and 1.60 liters of 2.50 times 10 to the negative 2 molar chloride are mixed together to form a 2-liter solution. Calculate the QSP and predict if lead chloride will precipitate, lead 2 chloride will precipitate or not. And then the KSP is given to us 1.6 times 10 to the negative 5. So then we calculate the molarity of lead ions, and then we'll calculate the molarity of chloride ions. So how does this work now? The way this is set up is that you get the molarity of the lead ions and how many you had in the 0.4. So this really is the moles of lead ions that you have in the solution divided by the total volume now. The volume has changed. So you have to calculate the new concentrations of these ions. So here the 0.5 and the 0.4 here, the 0.5 molar is the original molarity and 0.4 is the original volume. So molarity times liter gives you moles of the solution divided by the new volume gives us the new molarity of lead ions. We do the same thing for chloride ions, and the initial molarity was 2.50 times 10 to the negative 2, and the initial volume was 1.60. Divide that by the new volume and you get this concentration. So now your lead chloride, okay, is lead 2 plus and then the 2 chloride ions, okay. And so now for the KSP, which is lead 2 plus and chloride ions squared, is equal to 1.6 times 10 to the negative 5. That is the KSP, but you are calculating the QSP. So the lead ions that you have in the solution are 0.1 and the chloride ions that you have in the solution are 0.02, but you're going to square that because you have two of the ions. That's what the KSP equation is. And this is equal to 4.0 times 10 to the power of negative 5. So compare these two, and again your QSP is larger than your KSP. So if QSP is larger than KSP, then a precipitate is going to form. Okay, so the important thing over here for you was to remember to calculate the new molarities, okay, of the lead ion and the chloride ion because you're mixing two solutions over here. Let's look at what factors affect solubility now. The one factor that you already know that affects solubility is heat. Okay, so which means that if you have endothermic or exothermic reaction, depending on that, you can actually change the solubility of substances. And that one we're not talking about here in this topic. Here we're going to talk about two things, the common ion effect and pH. So common ion effect, and this is more like the Le Chatelier's principle. Le Chatelier's principle states that if you create a little bit of disturbance in the equilibrium, then the equilibrium will shift to compensate. So it might go backward or it might go forward to compensate for that little change. So what happens here is the presence of a second salt, if it produces an ion that is common to the solubility equilibrium, then it will reduce solubility, obviously, because an ion like that is already present, okay, and so it will shift the equilibrium backward. All right, so for example, if you add a little bit of silver chloride to a solution of silver nitrate, okay, so which means that silver and nitrate ions are already there, and if you add silver chloride, well, silver and silver then is going to become more, and therefore your equilibrium will shift backward. So that's kind of what happens, okay, and this is explained here also. The concentration of the product ion increases, and so the equilibrium is reversed, all right, and so which means that you form a solid. In that case, solubility is not increased, it's actually decreased, all right, by the common ion effect. And then there is a pH effect. So some salts, as you remember, are more soluble in acids or bases. Now, depending on what kind of salts you're talking about, and also even if you had strong acids or bases, those will be affected by pH as well. So if you have a hydroxide salt, it would be affected by pH, as in the addition of an acid will increase the solubility of a hydroxide. In the previous presentation, I had showed you or kind of mentioned to you the solubility of aluminum hydroxide, which was so less, okay, in water. But then if you add a little bit of acid, maybe it will increase the solubility. Okay, that's kind of what we're talking about over here. So it depends on the nature of the salt that you're talking about. So if the ion in the salt in the solution is a conjugate base, then acid will increase the solubility. On the other hand, if you have an acid in there, then the base will increase the solubility because the conjugate acid will start reacting with the base. If the acid is reacting with the base, that means the product is getting finished up. And if it's getting finished up, then you're forming more and more of the product. Okay, so the equilibrium is shift forward, and that is how the solubility is increased. So let's look at the common ion effect and see how that affects some of the solubility, okay? And so unless you see numbers, sometimes it's hard to imagine, okay, what's going on because it's all conceptual then. So let's look at this problem. What is the molar solubility of silver chloride in a 1 liter solution that contains 2.0 times 10 to the negative mole of HCl, hydrochloric acid? So then the KSP of silver chloride at 25 degrees Celsius is 1.8 times 10 to the negative 10. So the initial concentration of chloride ion is already there, okay, because there is already some HCl present in there. So then we're going to have to solve for X, okay, and find the molar solubility. The KSP is already given, okay, so we're looking for molar solubility. So let's look at this. Here is our equation where we have the silver chloride dissociating to give silver and chloride ions. Initial silver is 0, but chloride is already present there. Okay, we have 0.02 molar of chloride ions in there. So the change then is plus S and plus S, of course, because when you added silver chloride, you are adding more of the two ions. So now the equilibrium concentration is S and 0.02 plus S. Okay, so now in this case, we're going to go ahead and calculate for S because we don't know what S is, remember? Okay, so KSP then is equal to Ag and then chloride ions over here. So 1.8 times 10 to the negative 10 is equal to X or S over here times 0.020 plus S, okay, over here. That. So these two, okay, multiply those two. So now what we're going to do, okay, to make our life a little bit easier for us is we're going to go ahead and assume that S is negligible. Now, you can't do that for both of the S's because if you do it for both, then how will you calculate for S? But one S you can, okay? So the one that you're adding, that one you can go ahead and assume that is negligible like we've done for acid-base equilibria before. And so therefore 0.020 plus X is equal to 0.020. And you can see the solubility constants are so low that the difference might be in the 10th decimal place or the 9th decimal place. So then 1.8 times 10 to the negative 10 is equal to 0.020 S. Okay, and once that happens, you can calculate for S, and the S is 9.0 times 10 to the negative 9. So the solubility of silver chloride in water, KSP, is S squared, right? Which is 1.8 times 10 to the negative 10, and that is S squared, which means that S is equal to 1.3 times 10 to the negative 5 molar. All right, so AgCl in water is 1.8 times 10 to the negative 10. That is what is given to us over here. That is the normal solubility constant, okay, for silver chloride, and at that point S is equal to 1.3 times 10 to the negative 5, right? Because you're getting two ions here, so you have S2 over here, so you take the square root of 1.8 times 10 to the negative 10, and once you calculate for S, this is what you get. The reason to do this calculation is to compare this concentration which you have to the concentration that you just have right now with the chloride ions already in the solution. You can see the difference. 10 to the negative 9, 10 to the negative 5. 10 to the negative 5 would have been if it was just water, okay? But as soon as you had even a little bit of hydrochloric acid in there, the solubility decreased so much, okay? It went from negative 5 to negative 9, okay, which is like 3 zeros, okay, 4 zeros at the same time. So, which means the solubility is greatly depressed, okay, is greatly reduced when you have a little bit of hydrochloric acid present. So that is what this kind of calculation tells you, the common ion effect here, okay, is that if you have a little bit of the common ion in there, then the solubility is going to be so much different, okay, than what it would have been if that common ion was not present. Let's look at another problem, now this time using barium sulfate. So calculate the molar solubility of barium sulfate in 0.01 molar sodium sulfate. Sodium sulfate is already in solution and you're trying to add barium sulfate to that. So barium sulfate here dissociates to give you barium and sulfate ions. And so initial concentration of barium is 0, but sulfate is already present there coming from the sulfate ions here, so 0.001 molar. The change in the concentration would be plus S for barium and then also plus for sulfate coming from barium sulfate. The equilibrium concentration then is S for barium and 0.01 plus S for sulfate. The Ksp for the equation is barium and sulfate concentrations. Both of them are 1 and 1 mole each, so you don't need any raised to the power. And this is all equal to 1.1 times 10 to the negative 10. This is the Ksp value of barium sulfate, which I have to give you. Usually it's given right here in the problem, but in this case, it's just given over here. So you have to look it from the table in case it's not given to you. Okay, and in case it's not part of the calculation and you are supposed to have it as a data, then just look it up in the table. So the Ksp value is 1.1 times 10 to the negative 10. So here is our Ksp. We're going to go ahead and calculate for S. So S times 0.001 molar plus S. And again, we are going to go ahead and ignore this S over here because the plus S is going to be very, very small. It may be 0.0001, okay, so the fourth or the fifth decimal place. So you can go ahead and ignore this, which means that S times 0.001, okay, those are your two new concentrations. And this is all equal to 1.10 times 10 to the negative 10. So then you calculate for S, and S turns out to be 1.1 times 10 to the negative 7 molar solution. So if you were to calculate the molar solubility of barium sulfate using this Ksp over here, like we did previously in the previous problem, Ksp would be S square because you have 1 and 1 mole of each. So then S is equal to 1 times 10 to the negative 5 molar. So this is what it would have been if there was no sodium sulfate present, but because the sodium sulfate is present, the solubility went down almost 100 times, okay, using a little bit of sodium sulfate. So, which means you can actually change these things just by a little bit of ions. Right now, it may not be making any sense to you as to where we use these things, and I will try and explain that to you, but this is really an important part in order to understand that you can decrease the solubility of one salt by using another very soluble salt, okay, and so you can cause this one to precipitate out in case you don't want this. All right, and so solubility changes a lot with just a little bit of common ion. Now let's see how solubility is affected by pH. So an example here is consider two slightly soluble salts, barium fluoride and silver bromide. Which of these two would have its solubility more affected by the addition of a strong acid? Would the solubility of that salt increase or decrease? So the first thing you have to see is what kind of products would you get. So addition of an acid to barium fluoride will give you hydrofluoric acid, which is a weak acid. Addition of acid to silver bromide, however, will give you HBr, hydrobromic acid, which is a fairly strong acid. So it means that your barium fluoride is going to be more soluble in an acidic solution. Why? Because you're producing a weaker acid. Remember, the whole point of acid-base reaction is to give a weaker acid or a weaker base. So whatever leads to the production of a weaker acid or a weaker base is going to be favorable. So barium fluoride is going to be more soluble in acidic solution because it produces a weak acid. Silver bromide, on the other hand, will not be so affected by the acidic solution because HBr is a strong acid and it should not be a product then. Now I want to go over something which is a little bit interesting. It's called fractional precipitation. And fractional precipitation is a technique of separating out two or more ions in a solution. So once you know the KSP of each of those ions, you can then use that information to kind of separate them on their basis of their unequal solubility. And it's a very useful technique in lab also, and also in real life, especially for example in purifying water. So when you're trying to get out the heavy metals from water, in order to purify it, then you need to know the KSP value so that you can add exactly the right amount of substances to precipitate out the right amount of ions from there. So it's a very useful technique. And again, you use the KSPs to figure out what is going to be soluble in what. Okay, so let's look at an example over here. Separating the salts of chromium 3, calcium, and iron 2 ions. So if you have these 3 ions in solution, then how would you separate them? So the first thing you do is you look for a common ion that can help you separate them. Now it doesn't have to be common, but here I have all the hydroxide listed out for you. So for all the hydroxides, the KSP of all these 3 salts is very different. You want to use a KSP value that is very different. If you use something like 8.0 times 10 to the negative 6 and 7.5 times 10 to the negative 5, those KSP values are so close to each other that you might precipitate 2 ions at the same time. And if you're trying to see the concentration of just one ion in solution, then you want their KSP values to be far away from each other. So it's possible that they may not all be hydroxides. It's possible that maybe that some sulfide is more insoluble, some hydroxide is less insoluble or less soluble, and then some sulfate maybe. Okay, so depending on what kind of KSP you're working with and what chemicals you're working with, you can choose what chemicals you need to separate them out. So here, for example, if you had the 3 ions in the solution, you could add a little bit of sodium hydroxide to these solutions. The first ion to precipitate out would be, yes, the chromium ion, because the solubility is very low for it. So you separate that out by centrifuging the solution. Once you centrifuge that and you remove the chromium, then you go ahead and add a little bit more sodium hydroxide, and then you can separate out the iron 2 ions because that's next in line for the low value of KSP, and then finally you'll be left with only calcium hydroxide in the solution, which if you want to precipitate that out, you can add more sodium hydroxide or not, depending on what you're trying to do. So you can use the different KSP values to separate out ions. That's a very important technique in qualitative analysis. And then there are things called complex ions. Complex ions are complex, okay, which means that it's possible for some ions to form complex ions. Complex means that you have more than one thing in there, okay. Usually we learn about salts that have one cation, one anion, or even one cation and one polyatomic anion. But in case of complex salts, you can actually have more than one ion in there, and some of these ions are not even ions, they're actually neutral molecules like water, like ammonia. So it's, that's why they're called complex ions, because they end up forming all these kind of things. And so you have to actually study them in the lab at one time at least to figure out what kind of complex ions can be formed. And so the larger the ion, the larger the cation, the more capable it is of forming a complex ion. Small ions like sodium, calcium, they don't tend to form those kind of things. Besides, they also don't have multiple valencies. On the other hand, transition metals will have multiple valencies, so they're more capable of forming complex ion. The complexing agents, which are also called ligands, they're usually Lewis bases, which means that they give electrons. Okay, and why? Because again, you're combining them with something that is a Lewis acid, which means it lacks electrons. So these are Lewis acids and the ligands are the Lewis bases, and so things like cyanide ion, ammonia, thiosulfate, and then hydroxide, water, those are all going to be ligands. And then what happens is that you keep adding the solution, and so you end up forming what is called a complex ion. A complex ion sometimes you can't predict unless you study them. You can't predict that this is what is going to form. Okay, and so you have to actually do this in the lab to figure out different kind of ions will give you different complex ions. That's about it that I will do for complex ions. The nomenclature for complex ions is quite different. How you form them is quite different. How you calculate their formation is very different. Usually we have KSP for solubility product, or Kc for equilibrium constants. Here you have what is called Kf, which is the formation, okay, constant. And the formation constant will tell you how much of each you need in order to form the complex ion, okay, how much of each ions you need to form the complex ion. So for us, it's a little bit too much. It's not completely out of the scope, but I have other things to cover as well. So we're going to forego this. Okay, so if you get to inorganic chemistry, you're going to learn about complex ions. And here are some complex ion pictures. They look really beautiful. That's the nice thing about complex ions. Okay, that's probably one of the most colorful thing, okay, or the positive thing about complex ions is that they're very, very colorful. So here's the one for cobalt, and here's one for copper. In some cases, the complex ions may be solutions. In some cases, the complex ions may be not that soluble, okay, which means that they might be slightly cloudy or they might precipitate out. So the concepts that I want you to gain from this presentation is to be able to predict precipitation using solubility quotient, which is the QSP, and then predict solubility using the common ion effect and sum of the pH. If you change the pH of a solution, then how will the solubility change? Which means you need to know the KSP values, and you need to know the formation of strong acid, strong base, or conjugate acid, conjugate base.